Well, welcome everyone. This is seminar number 37, would you believe, of our series, Topics in Modern Physics. And today we're going to try something a little bit different. So instead of talking about just one topic, we want to talk today about as many of these 6 topics as we have time for. So each of these topics is a brief report. They're all new ideas. They all come from published in the last 6 months, 4 of them in the last 2 months. And they're on a wide range of different topics, as you can see. And none of them are sufficiently expansive as to fill up a whole 90 minutes, but each of them, I think, is worth a bit of our time. So we're going to talk about a new advance in possibly resolving what's called the Hubble tension. Then we're going to talk about some papers that have been written about the early molecules on Earth, the early Earth itself, and early humans. Then we're going to relate that to reports about what molecules have been found in outer space. Then we're going to find out how you can X-ray a volcano to see if it might be in the process of preparing to erupt. The next topic is a discussion of how many hours there will be in the day and in the future. And lastly, there was a note which explained how the computer that ran the Apollo mission was working, how it was comprised. So we'll start with the first one, and please feel free to jump in anytime and ask questions, because we're going to cover a wide range of different topics, and so don't wait to the end. So the Hubble tension has to do with measuring the expansion rate of the universe. And on this graph, we have vertically the distance that light has traveled to reach Earth from whichever object we're discussing versus the redshift, the change in the color of that light, which has to do directly with the expansion of the universe. So if the universe was half as big as it is now when that light was emitted, then the redshift will be 1. And the frequency of that light will be half as much as it was when the light was originally emitted. As the universe doubles in size, the wavelength of the light doubles also, and so the frequency is cut in half. So if you measure a bunch of distant objects, let's say supernova, and you measure how far away they are, and you measure the change in their light, and you have a series of points, and you end up being able to define a curve, then what we're interested in is the slope of the curve now. How fast is the universe expanding now? Earth is at the center of this coordinate system. And so Earth is at distance 0 and at redshift 0. So the question is, what is the slope of this expansion curve at this moment in time? And that number is called H0. H is the Hubble expansion rate, and 0 means today. Okay, so the tension, the problem is that we can measure H0 in 2 very different ways. It's the same thing, so we should get the same result in both of those ways, and we do not. So if we measure the properties of the universe as we see it now, which is called the late universe, the universe of today, we measure distances to the sun, we measure the distance to the nearby stars with parallax, we find Seifert variables that have known brightness, so we know their distance, then that helps us identify the brightness of supernova type 1a, and then we can compare that to other supernova type 1a, and we measure their distances and so on. So this is the local distance ladder. We build up a measurement system rung by rung, starting with the Earth and moving backwards in time and out into space. And if we do that, we find out that the expansion rate in these crazy units is 73. The other approach is we take a measurement of the universe at almost the very beginning of time, where we can make a very precise measurement. And then we extrapolate back 14 billion years to today using our theory of cosmology, which is the lambda cold dark matter theory. And we get the expansion rate today, which is about 68. And 68 is not equal to 73. The difference is 5 something, which is about a 7.6% difference in value. And 10 years ago, the measurement uncertainties were quite large, and it wasn't clear that the numbers were truly different because the errors were very high. But now, as everything has gotten to be much more precise, we can say that this difference of 5 is not a statistical fluke. This is showing us some real effect. In fact, the odds of this being a statistical fluke are less than 1 in a million. It's approximately a 5 standard deviation discrepancy. Now, it could be that someone has made an error in the measurement, either here or here. It could be that the theory is wrong, or it could be that there's some underlying physics that we haven't understood. But there is something to be understood, because this is not just a statistical variation. Well, we've been struggling with this for probably about 15 years. It's gotten worse and worse as the experiments have gotten more and more precise. And just this last January, a very interesting person from a very interesting university, we'll talk about that later, published a really remarkable paper that may resolve the issue. So he highlights a number of things that have been well known in the past by many people, but he is much more comprehensive in his analysis, and he is able to calculate things that have never been calculated before. So let's start off with what the issue is. Our lambda cold dark matter theory, the currently accepted standard theory of cosmology, assumes that general relativity, Einstein's theory of gravity, is correct, and that our universe is perfectly isotropic and homogeneous. In other words, it's got the same energy density more or less everywhere, and it looks the same in all directions, more or less. And we make that assumption because that's the only way we can solve the equations. No one has ever solved the equations of general relativity for a system which is inhomogeneous and not isotropic, anisotropic. So if you had a universe with a bunch of mass on one side and less mass on the other side, that would be inhomogeneous. No one has been able to solve the equations of general relativity for that sort of a system, which is why we assume that it's perfectly smooth and homogeneous. But we know that that's not really a great assumption because the universe may be homogeneous on very large scales. If you take a million light year box, a million light years by a million light years by a million light years, I'm sorry, let's say a billion light years by a billion light years by a billion light years, then that box will be pretty much the same as any other similar box you might be able to find anywhere in the universe. It have about the same number of galaxy clusters and so on. But if you look at smaller scales, like a cluster of galaxies, it's clearly not homogeneous. The galaxies are in different specific places, and they're not smeared out all over the space. So, and if you look at the solar system, 99.8% of the mass of the solar system is in the center, in the sun. So that's not homogeneous at all. In fact, the universe is almost completely empty. And here and there are clusters of galaxies. And within those clusters, it's almost completely empty, except here and there are galaxies. And galaxies are almost completely empty, except here and there are stars. So it's really very inhomogeneous on small scales. So we have made an assumption in doing the math, which clearly isn't correct, except maybe on the largest size scale. And these are a few numbers to give you a more quantitative feeling of how different things are. The average energy density of throughout the universe converted into mass is this number here, which corresponds to about 6 hydrogen atoms per cubic meter. Cubic meter is 37 cubic feet. So that is almost completely empty. The galaxy cluster that we are located in, which is cleverly named the local group, has an energy density that is 100 times greater than the energy density of the universe overall. And if you get even closer to home and you talk about our Milky Way galaxy, then that is another factor of 100 more dense. So it's 10,000 times more dense, the Milky Way, than the universe overall. So it really isn't that homogeneous. Now, when physicists end up in a situation where they can solve the ideal case, but they can't solve the real case, they have a number of tricks in their bag. And one of them is called the perturbation method. So this works if you have a system that's almost ideal, but has a slight twist to it, a small perturbation, and we'll call that perturbation X. So we can solve the case for X equals 0, no perturbation, that's F sub 0. And we can't solve the case in the real situation because we just can't do the math. So we write this is what we really want to calculate. This is what we can calculate. And all of these terms are the discrepancy that this perturbation causes. And you can express any function in terms of a power series like this. So this is no magic. And this power series runs off to infinity. So this perturbation method is useful if X is very small. And so these terms are getting small fast enough that hopefully you can ignore everything to the right. And then we can focus on calculating or trying to calculate one or two of these terms here. So that's the general technique. And people have tried to use that perturbation method in the analysis of the universe. And in 1976, the Nobel laureate Steve Weinberg, about whom there's a cute story, was able to demonstrate with a certain number of assumptions that this leading term here, the F1 was 0. So everybody got very excited about that and decided, well, we can just ignore all this stuff and talk about the universe as if it was ideal. That turns out to be a bad assumption. Okay, so this paper that was published in January focuses on things that people had known before, but not really pursued to the extent that he did. So he makes several points. First is that we are viewing the universe from a location which is not typical of the rest of the universe. So our viewpoint is uncommon. We are in an extremely dense area, a concentrated area of energy, because we exist in a cluster of galaxies, which is 100 times more dense than the universe overall. So this is the local group. Most of the mass of the local group is believed to be in a halo of dark matter, which I show in black. That's about 84% of the total mass of the local group. And the local group has the Andromeda galaxy and the Milky Way galaxy, which are major, beautiful spiral galaxies. And it has 80 minor galaxies that all add up to only about half of either one of these two. So it's almost entirely two big galaxies plus the dark matter. And As light from some distant object, let's say there's a supernova out here halfway across the universe, as light from that supernova comes toward us and enters the local group, this highly concentrated region of mass and energy will bend the light. Gravity bends light, as Einstein explained. And so the light will be focused to some extent. And also, as the light drops into this gravitational potential well, its frequency will increase. So if you drop a rock from the mountain, it goes faster and faster. Its kinetic energy becomes higher and higher. If you drop light down into a gravitational potential well, it can't go faster, but its frequency increases. So its energy increases just like the rock does. So we have two effects. The light is focused, so it looks brighter, which we interpret as if the supernova was actually a little bit closer than it truly is. And the light is blue shifted, so it has a lower degree of redshift. The redshift lengthens the wavelength, reduces the frequency. Blue shift is the opposite. So if you blue shift it, you're cutting the redshift down. So that we interpret as meaning that the object occurred at a later time in the age of the universe. So the effect of these two factors is to move, let's say that the real object was located here, then since it looks brighter, we think it's a little closer, so the distance is less, and also the redshift is less. So we've moved in the direction that the line is moving in anyway. So far this effect might just be moving these points around a little bit, but not changing the line, and therefore not changing the slope. So maybe Weinberg was right that it doesn't make that much difference. But they don't cancel exactly, as this paper shows. The second point the paper makes is that we have calibrated the brightness of supernova by observing supernova within our local group. We calibrate that supernova brightness because we see supernova that are in proximity to Seyfert variable stars, and we think we know the brightness of those. So we have used the local distance ladder with radar and parallax and Seyfert variables to calibrate supernova that are very close to us, and they've only been a handful that we can look at. And then we use that calibration and apply it to supernova that are in very different places. They are not necessary, they're not in the local group. They're in some other star systems maybe, or maybe just out in space. And so the calibration that we've made makes certain assumptions, and then we apply it to very different situations. So that's an inconsistency in our logic. Anyway, so this guy is named Obina Umuth. That's the best picture I could find of him. And he published this paper in January. He's at the University of the Western Cape in the Republic of South Africa. I read about or skim through the abstracts of about 300 astrophysics papers a week. And I've been doing it for a few years. And this is the first time that I can recall ever seeing a research paper from sub-Saharan Africa. So this is a remarkable event in and of itself, that such an extraordinary paper gets published from such a seemingly unlikely source, but it's very encouraging that it is. So Dr. Umuth has gone through all of the things that people did before, and indeed, but now he has been able to do the math much more effectively than anyone had done before. And he confirmed Weinberg's initial idea that this F1 is either 0 or a very small number, but he was able to calculate F2 analytically, and for a general case. And he showed that F2 is substantial, is a substantial number. It's not zero, and it has a big effect. And he calculates how big the effect is, depending on the size of the galaxy cluster that you're talking about. And this gray zone is our best estimate of how big our galaxy cluster, the local group, is. And so he says that this can all amount to either a 8 or 12% effect, and in the exactly the same direction of the error that we find between the early and late measurements of H0. So it's very, you would have to do a detailed calculation for each supernova, because the light comes in from different angles and traverses different parts of the local group. So the numbers are going to be somewhat different, which would be extremely tedious. There are many hundreds of those supernova. So he didn't completely resolve the issue, but he has shown that there is an effect that hasn't been addressed before, which can explain the entire difference. So both measurements may indeed be correct. They're just not quite measuring exactly the same thing as we thought they were. So anybody have any questions about all this? You guys aren't excited about this so much, but let me assure you that the world of astrophysics is abuzz. Now, it's only been 2 months, so he hasn't been raked over the coals in the usual fashion by all of the critics, but that will certainly happen. Yes, Andrew.
So as the light traverses from supernova far, far away, it must transition through a host of local groups, right? So the ultimate frequency you would think would be compounded as it travels through these various groups, making it almost impossible to calculate.
Well, it would certainly be very difficult to calculate. The two things that I would say about that is the universe is almost completely empty. So when we're looking at these supernova, almost never is there anything else along the line of sight. You could shoot a bullet across the universe and it would probably not hit anything. That's how empty it is. Secondly, if the light was to go in and out of an intervening cluster of galaxies, it would be blue shifted as it went in and red shifted as it went out. So it would come out with the same frequency as it went in at. Now,
okay, let me think about that. Okay.
Well, and if you let a rock drop to the bottom from the top of a mountain to the bottom of a valley, and if it bounced, it would come up and it would stop at the same height, right? If in a perfect world.
Right. Okay. Okay.
So that's about what the light is doing. It loses it gains energy going in and loses the same amount of energy coming out. Anyway, this will be argued about for 10 years at least, and other people will go through his math with a fine-tooth comb. I mean, not just other people, I'm talking about hundreds of other people. And he will be raked over the coals, as I said, by all of the critics. And eventually, if they don't knock him down, then God knows, he could win a Nobel Prize. I'm rooting for him. Okay, next topic. There are a series of papers that all relate to the original condition of the Earth, of where organic molecules come from, and something about the evolution of mankind. So I lumped them all together in this one topic. We'll start with the organic molecules. The key molecules of life are amino acids, and in our DNA and in the DNA of every living thing that's ever been examined, The DNA is comprised of combinations of these 4 amino acids, which are abbreviated A, C, G, and T. And these define how proteins are constructed. The proteins use more amino acids than 4, up to about 20. Some forms of life use a slightly different set, so the total number is 1 or 2 more than 20, but 20 is the ballpark. Okay, so that's not a terribly large number, 20. For all the proteins, the millions of protein, a million proteins plus in the human body, this is not such a big number. Okay, the search for how these organic molecules get created, come to be in the first place. The most notable origin of this search is an experiment by Miller and Urey in 1952. Harold Urey won the Nobel Prize for something else. He and his graduate student, Stanley Miller, concocted this flask filled with the gases they thought the early Earth contained. They exposed it to sparks, which is the substitute for lightning. They passed the gas through cycles of cooling and heating, night and day. And after a few days, they got this goo that Mr. Miller is staring at down here. And when the goo was analyzed, it contained a number of different molecules, including 4 amino acids. Not the 4 amino acids that we use in our DNA, but nonetheless 4 of the 20 amino acids. And it was thought in 1952 that all we had to do was tweak this experiment, run it longer, whatever, different temperatures, different gases or something, and we would end up with all of the molecules of life. That they would all be, we could demonstrate that they could all have been created spontaneously by random chemical reactions in the early Earth. Well, the experiment has been repeated probably 100 times in all sorts of different circumstances, and we've never gotten more goo than they did in 1952. So we have never been able to make any appreciable portion of the full set of 20 amino acids in this way. Not to say that it wouldn't happen eventually, but in half a century or more, we haven't succeeded in replicating that chemistry. Okay, now we have looked for molecules in outer space, in distant stars and galaxies, and we have found a total of 256 different types of molecules. We find these molecules in outer space by looking at the color of light that they absorb. This is called the science of spectroscopy. And this is the research paper reference to that 256. 5 of these molecules were molecules that were unknown to chemists on Earth. They don't exist on Earth in any form that we have found. 10 of these molecules were found in the galaxy 6 billion light years away, which is nearly halfway across the universe. And 12 were found in a quasar that was even farther away. These were molecules that had to be created, let's say, within the first billion years of the age of the Earth. So molecules are out there. These molecules included carbon rings. Benzene is a carbon ring with 6 carbon atoms. Some of these molecules had as many as 10 carbon atoms in a ring. And the most complex of these molecules, the chemical formulas are listed here for the 2 most complex, but none of the 256 molecules were amino acids. Again, that doesn't mean they don't exist out there. We just haven't found them yet. And we have certainly been looking. So they're rare, I guess.
I have a question.
Yeah.
In that original experiment, that he said you said those were the original diagram that you put up. It said those
Yeah.
that this H2O, CH4, H2CO. How did they select those? I mean, if they select something different, would there be different kinds of amino acids?
Possibly, and that's part of what the other 100 experiments tried to do.
I see.
This is water, methane, ammonia, hydrogen, and carbon monoxide.
Yeah, carbon dioxide. Yep.
And people who worry about these things and study these things felt that these were the most likely gases to be on the early Earth. That's really a guess.
Yeah, it is.
And one thing they have in common is they're all quite simple.
Right.
They have 3 and 5 atoms. They're not some terribly complicated structure to begin with.
So
you can certainly find all of these gases. You can find these molecules in space very readily. These are commonly produced in the cosmos.
yeah, I remember you telling us that a while back, a long time ago. Yeah. Okay. So the 256, none of them are amino acids.
Correct.
Does that mean that we're the only ones that have amino acids?
We are the only place that the amino acids have been found. People are looking, there's probably 100 billion planets out there in the universe, and we won't be able to look at all of them, but it says that they're rare. Just how rare you can argue about, but they certainly are much rarer than people originally thought. I like to make the argument that we're actually special.
Well, I know your argument, and that seems to add to it, right?
Yes.
I don't think you covered that in your book that I just
Oh,
read.
no, well, this was published 2 months ago.
Ah.
See, I'm bringing you right up to the current state of the art as it is. Okay, so let's talk. We talked about the early molecules. Let's talk about the early Earth itself. This was published in an online journal called Quantum Magazine, which is amusing. It's particularly mathematically oriented, and it's free. 2 reasons I subscribe. Okay, so they discussed the discovery of zircons, which are a mineral, a cheap form of diamond, if you will, that were found in what are called the Jack Hills of Australia. So this is the western end of Australia. And these rock formations at the western end of Australia seem to be undisturbed since the beginning of the Earth. Most of the Earth's surface has been remodeled by plate tectonics multiple times, so it's hard to find really old rocks on the surface of the Earth, but the Jack Hills have the oldest rocks that have ever been found. And therefore, they have the oldest fossil evidence that has ever been discovered. So these zircons are a very tough mineral, and what gets trapped in the zircons when they are originally formed stays there for billions of years because the mineral doesn't allow anything to get in or out. And we can go back, these zircons, the formation of these zircons occurred very early in the history of the Earth. And the earliest one is listed at 4.4 billion years. The age of the Earth is 4.569 billion years. So that's almost the beginning of the Earth. And there's convincing evidence that liquid water existed on the surface of the Earth almost immediately after that. And there is evidence of life in the form of what's called organic carbon, dating back 4.1 billion years. Now, organic carbon is an iffy topic. Carbon comes in different isotopes: carbon-12, carbon-13, carbon-14. Carbon-14 is radioactive. We use it for dating. Carbon-13 is about 1% of all the carbon on Earth. Carbon-12 is the 99% of the carbon on Earth. And life forms in general seem to prefer carbon-12 to carbon-13 because of the mass difference. It's easier to do chemistry apparently by some amount with carbon-12 rather than carbon-13. So certain scientists argue that if you find an object that has an abnormally large ratio of carbon-12, more than the typical 99%, that's an indication that it is a fossil relic of living thing. There are a lot of assumptions in that line of reasoning. So that's why I put the quote marks around organic. From a chemist's point of view, all carbon is carbon, and you can't tell if it's been in a life or not, or at least from a physicist's point of view. From a biologist's point of view, they make that distinction. Okay, then I also note, this is a different paper, I don't have maybe it's the same paper, that people have analyzed meteorites that have fallen on Earth, and there was one that's been dated to 2.7 billion years ago. That's the formation date of the meteorite, not when it landed on Earth. And because of the burning of the outer crust, they can show that the Earth's atmosphere 2.7 billion years ago, when the meteorite came through the atmosphere, had to have about 70% carbon dioxide, which is an enormous amount of carbon dioxide. It's Venus and Mars have carbon dioxide that's in that range, and boy, they're a bad place to live. But anyway, the current level of carbon dioxide in the Earth's atmosphere is 0.4%. So this is an enormously large number by comparison. And this would cause a huge amount of global warming. I mean, people get excited about 0.4% changing by a small fraction, but can imagine how excited they would get if it went to 70%. But others argue that that's exactly what we needed to have life on and liquid water on Earth back then, because the sun wasn't putting out as much energy as it is now. So the Earth would have been much colder, and without this 70% oxygen in the atmosphere, there would not have been liquid water, which clearly there was. Anyway, there's another factoid for you. Now, switching again to a different side of the early Earth discussion, these two scientists, Rebecca Martin and Mario Livio, published a paper. This is last month, February of 2020, and sorry, 2022. And you've probably seen Mario Levy on the TV many times. He's sort of the spokesperson for the Hubble Space Telescope, or had been for many, many years. So he's, you may not remember the name, but you probably would recognize his face if you saw him. Anyway, these two published a paper, and the paper highlights the importance of asteroids to the existence of life on Earth. Also something I mentioned in my books. So they note, with a fact that's been well accepted, that asteroids bombarded the Earth very heavily in the past, and particularly in the first billion years. There was sort of a chaos in the solar system as it formed, and a lot of the asteroids that originally formed in the asteroid belt were knocked out of their orbits by the heavy planets Jupiter and Saturn, and fell to the inner solar system, and some fraction of those hit the Earth. Most of them just fell into the sun, but some fraction hit the Earth. And it is assumed or believed by people who worry about the formation of the Earth, that we have water in great abundance on the surface of the Earth because it was brought to Earth after Earth stopped being a molten ball of rock. When Earth first formed, it would have been a molten ball of rock because of the immense heat of the formation process, the gravitational potential and energy release as all of these rocks accreted onto each other. Any water that existed prior to that would have been certainly boiled away and dissociated. The hydrogen would have floated off into space and that water would have been lost. So water had to come to Earth after Earth cooled down enough so that the surface was below boiling point. And we looked to asteroids to be the source of that water. And they also brought iron, which is common element in solid objects in the cosmos. And the impacts and the release of these elements caused the atmosphere of the Earth to contain a substantial amount of hydrogen. And hydrogen atoms react very aggressively with other atoms. So that spurred the development of molecules, and in particular spurred the development of hydrogen cyanide. And hydrogen cyanide is well known to people to be a very nasty toxin, poison, but it is also the precursor in biochemical processes to the creation of amino acids. So if you want to make an amino acid in a chem lab, you're going to typically, you would often use hydrogen cyanide as a starting point to make those amino acids. So not only did we get the water, we got some more iron, which is important to the magnetic field of the Earth, but we got a chemical process to lead to perhaps amino acid production. So their conclusion is that for life to exist anywhere else in the universe, you need a planet in a star system that has an asteroid belt, and you need to have a means by which the asteroids are going to be driven out of their orbits and bombard the inner terrestrial planets, like a substitute Earth, Earth 2.0. Okay, so these astrophysicists, Martin and Livio, do some calculations, and they try to find out what it is that creates asteroid belts and what it is that creates this driving force to cause the asteroids to bombard the inner solar system. So first of all, they say you need giant planets outside the snow line that prevent the formation of terrestrial planets just inside the snow line. So the asteroid belt exists because a planet couldn't form in that band because of the gravitational influence of Jupiter. Mars exists barely. It's a very small planet, but it's further away from Jupiter than the asteroid belt. First thing is you need the formation of giant planets beyond the snow line. The snow line is where water condenses into ice in the vacuum of outer space. It's not the same temperature as it would be on the surface of the Earth, but in the vacuum of outer space, ice is formed at 170 Kelvin, which is minus 150 degrees Fahrenheit. Now, the thing that they discover is that it's actually not just Jupiter's motion that displaces these asteroids and drives them into the inner solar system, but it's a specific resonance of the planets Jupiter and Saturn that has that effect. One planet by itself would not dislodge all these asteroids. It's estimated elsewhere that 99% of all of the original asteroids in the asteroid belt were driven out by Jupiter and Saturn And that was the cause of the original heavy bombardment. And it's only the 1% that we see today that are the leftovers. Anyway, they go through some complicated celestial mechanics, and they show that if there's a specific resonance, which is called nu-6, of these two giant planets, they have different orbital periods, and they also, their orbits will precess in some way. So you need a specific combination, which is called the nu-6 resonance. And that is the effect that drives asteroids inward. Other effects would drive the asteroids out of the solar system, which wouldn't do us any good. So it's only a particular resonance of this two-planet system, they claim, that's responsible for the bombardment of Earth by asteroids. And they went through all the known planetary systems that have been discovered beyond our own. And there are 3,629 planetary systems that we have discovered so far outside of the solar system. And the big planets are easy to spot. So they went through and they looked at all the big planets in those planetary systems. And they found that only 4 of the 3,600 have a strong nu-6 resonance comparable to the one that we have in our solar system. So this is an explanation for the fact that this is only 1 in 900 known planetary systems have a nu-6 resonance that could drive asteroids into the inner planets, which they decided was essential to the existence of life. It was another thing that makes us special. Okay, now let's talk about a interesting paper that discusses the evolution of human beings and the planet Earth. And this comes from Hofer and Loeb. This is the reference. Again, it was published last month. Avi Loeb was for a great many years the chairman of the astronomy department of Harvard University. So he publishes all sorts of wild, crazy ideas, at least one a month. And I read them all because they're all creative. They may all be nonsense, but they're all very creative. Anyway, so this is his February version. He says that some of the ice ages on Earth are due to cosmic reasons, not just the reasons having to do with the solar system and Earth itself. So these two authors say that as the Earth and the sun, as the sun rotates around the Milky Way galaxy, it is moving through the material of the galaxy, the interstellar medium, at some velocity. It's not moving at exactly the same velocity as everything else, like a Ferris wheel. It's moving through that medium at about 26 kilometers per second, which is the Earth's velocity orbiting the sun is 20 kilometers per second. So it's in the same ballpark. And as the sun goes through all these different parts of the Milky Way, it passes through what they call hot clouds and cold clouds. And these aren't what you would think of as being clouds, but these are hot and cold balls of gas that are quite different. The hot balls of gas have been created by supernova explosions. The cold clouds are what you have if there is no source of heat. So the hot interstellar medium has a temperature which is greater than the temperature of the surface of our sun, which is 5,000 Kelvin. So this is 8,000 Kelvin. And the cold is 20 Kelvin. So this is what, 400 times more? Big difference. And the density of material has an even bigger difference. So in the cold clouds, the material condenses more, it becomes much more dense, and you have 3,000 hydrogen atoms per cubic centimeter. This is in the Milky Way, where, as we discussed earlier, the density of material is much higher than in the universe at large. And in the areas which have been heated to a very high temperature by supernova explosions, long past, excuse me, I'm trying to kill my mouse. There's only about 1/5 of a hydrogen atom per cubic centimeter, so an enormous difference. And this difference, Loeb says, causes big changes in our solar system. There we go. Mouse still works. Okay, so they claim that there are these alternating bubbles, clouds of hot and cold gas in the Milky Way. And as the sun proceeds through it, the sun passes from one hot zone to a cold zone to another hot zone and so forth. And we are now in this hot zone, which is cleverly named the local bubble. And this is an area of warm gas, thousands of degrees Kelvin, but very dilute gas. And we have been and we will be in the future passing through areas that are very cold by comparison. So we are in the solar system protected from the vagaries of the galaxy by what is called the heliosphere. This is the heliosphere is the volume of the Milky Way that's dominated by the effects of the sun, including its solar wind and its magnetic field. And that heliosphere protects us from a large number of galactic cosmic rays. So the magnetic field of the sun deflects about 75% of all of the cosmic rays produced by the galaxy, many of which would come from supernova explosions. It deflects 75% of those cosmic rays that have energy less than 200 million electron volts. The mass of a proton is 900 electron volts, so this is not such a high energy. When we go through the cold clouds, according to the authors, the heliosphere shrinks dramatically. So the heliosphere currently is about 130 astronomical units. That's 130 times the astronomical unit AU is equal to the size of Earth's orbit, the radius of Earth's orbit. So 130 times is far beyond the reach of the planets, but it's still within what we consider the solar system. So when we go through a cold cloud, that heliosphere shrinks all the way down to 1/4 of the size of Earth's orbit. So we are then exposed. We have lost that shield during the periods in which we are in a cold cloud. We are protected when the solar system is in a warm cloud. Now, the evidence that they have for this is that supernova produce all sorts of radioactive isotopes of all sorts of elements, heavy elements, including iron-60 and plutonium-244, which have relatively short half-lives in a geological frame of reference. So this is about 3 million years, and this is 81 million years. Not a million years seems like a lot, but that's much less than the age of the Earth, which is 4.5 billion years. So the fact that we have found these exotic radioisotopes at the bottom of the ocean and in the ice of Antarctica and also on the moon indicates that they have arrived relatively recently. certainly much later, much more recently than the creation of the Earth and the Moon originally. So these isotopes could not have, they would not still be around if they had come originally with the formation of the Earth. So we had to be exposed to supernova explosions in order for these isotopes to be found on Earth. And they believe that the explanation is that only when the heliosphere shrinks are we exposed to this cosmic radiation that comes from supernova explosions in other parts of the Milky Way. And by measuring the amounts, the relative amounts of these isotopes, they can calculate when these isotopes arrived on Earth. And from that, they decide that we have passed through two cold clouds, one 2 million years ago and the one before 7 million years ago, and others presumably even before that.
Does that coincide with the killing of the dinosaurs?
No, that was 67 million years ago.
Okay.
They get something else. They were killed by probably an asteroid, but maybe a comet.
That's what I heard.
So
But
that's
this new theory. So
that's within our solar system. These are all people's ideas of what happened in the past, right? We don't have a video image of that happening.
hypotheticals.
Yes, hypothetical, yes. So to conclude this crazy idea, when we pass through a cold cloud and the heliosphere shrinks, that changes the climate of the Earth, and it causes, they believe, the climate to become much drier and also much more erratic. And they say that that may have contributed to the demise of one of the humanoid ancestors of Earth, of Homo sapiens. These are humans that, humanoid creatures that existed 3 million years ago, and they were called Australopithecus. As Gil and I were discussing at the beginning, there is one fossil that has been discovered, the first fossil evidence, maybe the only one, of Australopithecus was discovered by the Leakeys, and they named that fossil Lucy. So this is the famous Lucy, the Australopithecus, one of the first humanoid ape creatures that walked on 2 feet. And with the demise of Australopithecus, there was room in the landscape for the rise of a new species, a new genus, and the new genus is Homo, that's us, starting with the species Erectus and on and on and on, and eventually with Homo, resulting in Homo sapiens, which is really us. And we are the survivors of all of this stress. You know, this creates climate stress. The species that can't cope are history, and we are the ones that survive because we do a much better job of adapting to severe environments, particularly the cold. So the last ice age eliminated various other human lines like the Neanderthal, and Homo sapiens are have inherited the Earth. Okay, any questions about these molecules and the Earth and humanity? Okay, moving right along. Let's talk about X-raying a volcano. So this is a paper that was published also relatively recently. And this a bunch of Italian physicists have X-rayed the volcano Mount Etna Mount Etna is the tallest volcano on the Eurasian plate and on the Eurasian main continent. And this is the altitude of 3,357 meters above sea level, ASL, above sea level. And this is an aerial topological map of the volcano. This is the central crater, CC. This is the northeast crater, NEC, southeast crater, SEC. If you have trouble remembering that, just this is the Southeast Conference football, American football, SEC. And why would they want to bother doing that? Or what's their excuse for having fun doing this? And that is that there are many towns, the largest of which is Catania, with a population of 300,000 people that are sitting at the base of this volcano. And it would be nice if it was going to erupt to give them a little bit of notice, so they could move a little bit farther away. So the muon Etna volcano analysis machine is, this is a picture of it sitting on the side of the volcano. It's called MEV, and it's located in this position where it can look at these craters. So how do you X-ray a volcano? Well, you use nature's cosmic rays. So cosmic rays rain down on Earth all the time from outside, many from the sun and many from the galaxy, and even a few from galaxies beyond the Milky Way. And the most prominent particle that manages to reach the surface of the Earth from outer space is a muon. It's a heavy version of electrons, and it has a relatively long half-life, so that allows it to reach the surface of the Earth. And this green track is a muon, which is coming down from the cosmos, not vertically down, but it's at a downward slanting angle. And they set up these detectors, which are the yellow objects here. It's a series of bars. They have 99 bars running vertically and 99 bars running horizontally. And there are 3 sets of 99 pairs of these scintillating bars. And each bar has a fiber optic at each end. So you can calculate that that's an awful lot of fiber optics. And these are all the fiber optics going into one photomultiplier tube, which has 64 channels, which isn't enough for all of these, but they merge many fiber optics into each of the channels. So anyway, they have a photomultiplier that's collecting data, and depending on which channel in the photomultiplier gets excited, they can identify the trajectory of the muon. And they're looking for muons that are going more or less downward and have passed through the volcano. So if the volcano is out to the right, then this is a muon that might have passed through the volcano. If the muon was coming in this way, then it would not have passed through the volcano, but there would be an equal number of those. So we can use the fact, we can count the number coming down from the left, and we can compare that to the number coming down from the right, that if you extrapolate backwards, would it pass through the volcano? And that gives you a measure of what fraction of these muons got absorbed by the volcano. So that's how you take an X-ray. Your body, particularly your bones, absorb more X-rays than your flesh. And so when you take an X-ray, the bones look white because they're not exposed. Okay, so this is the results of their first 3-year trial run. They did a trial run to try to justify to the Italian government that it should spend more money to build a more comprehensive device to protect the citizens of Catania. So these on the left and on the right are 2 images taken probably from Google Maps, taken from satellites of the top of Mount Etna. And the image in the center is the image that's taken by this device, the X-ray of the crater. And they discovered in 2017 that there was a gap, a cavity under the main crater. This is a higher concentration of X-rays than than the rock around it. So that means that there's void space here. The X-rays weren't absorbed as much in this area as they were in the immediately surrounding area. So this is a void space. And indeed, after this picture was taken, the crater collapsed. All this rock fell down into the void, as you can see here. So if you saw a void and it filled from the bottom, then that's lava. And if the lava is filling the cavity, then the next place for it to go is out and run down the side of the mountain and cause chaos below. So this is a demonstration that they can actually make a measurement of something meaningful and hopefully protect the population. This was something similar was actually done 60 years earlier by Louis Alvarez, the Nobel Prize winning particle physicist from the University of California, Berkeley. And he used a somewhat cruder system. Back then, they didn't have computers to analyze all this stuff. So he X-rayed the pyramids. He X-rayed the Great Pyramid of Gaza, and for the purpose of looking for hidden chambers. And I don't know if he found any or not. His results were nearly as clean as these, which aren't terribly clean anyway. But so these Italian physicists didn't invent this idea. They adapted what Louis Alvarez tried to do with the pyramids to address a problem that is more socially impactful. Any questions about this? Moving on. Okay, well, do you ever get the feeling that there just aren't enough hours in the day? Maybe we can solve that. So let's talk about how long it takes the Earth to spin. What makes 24 hours? There are two official measurements, time standards that are internationally adopted. One is called universal time, and that is determined by 1 Earth day is the time it takes for the sun to reach the zenith in the sky from one event to the next. And that's called universal time. Terrestrial time is defined as a certain number of standard international seconds. So 24 times 60 times 60, standard international seconds is equal to 24 hours equals 1 day. We typically operate with terrestrial time since everybody's got a clock that measures seconds, not the position of the sun. And the standard international second, of course, needs to be defined. And it used to be something to do with the length of the year in 1900, but now it's defined in terms of an atomic clock, which is much more stable, and 9 and some billion oscillations of the frequency of the radiation emitted by this atomic clock, cesium-133, is the definition of a standard second. So this is a relatively long wavelength radiation, which means it's a relatively low frequency. Most light has much higher frequency, but even higher than 9 billion oscillations per second. But this is easier to measure, I suppose. Still not easy to measure. You're talking about measuring 1/10 of a nanosecond. That's certainly doable with modern electronics, but okay. So we have those definitions of time, and it has been known for quite a while that the rate at which Earth is spinning, which defines one day, is getting longer and longer. The Earth is not spinning as fast now as it did in the past. And presumably it will be spinning even slower in the future than it is now. So there will be more time each day in the future than we have today. Not a lot, but definitely more. So according, there's actually an organization, international organization that worries about this. And they are called the International Earth Rotation and Reference Systems Service, IERS. And they worry about the LOD, L-O-D, the length of the day. And their proclamation is that the length of the day is increasing by about 18 microseconds every year. Now, that's not a lot. If you live 100 years, that's still 18 milliseconds. That's not much of it's 2 milliseconds. It's not much of an improvement, but nonetheless, the day's getting longer, according to them. That's the reference. This is last October, 2021, the 10th month. Okay, and this is the plot that they have put together. This is the actual length of the day, the green thick line curve. And you notice that it undulates quite dramatically. So the length of the day is getting longer by a substantial rate during this period. And then for several centuries, the length of the day, almost 1,000 years, the length of the day is more or less constant, and then it ramps up again, and then it's more or less constant, and then it ramps up again, and right now it's more or less constant, but it's expected to ramp up again. So the long-term average is this pinkish band, and that's what 18 microseconds per year looks like. And right here you see the newest data in the thin black line, and that's shown in greater detail here. And so the length of the day really is rather erratic, and it's is rather erratic because many different factors influence the length of our day. But for the last approximately 60 years, this is 2020 over here. The last edge of the graph is 2020. You can see that the length of the day got, let's say, 3 milliseconds longer, then 3 milliseconds shorter, then 4 milliseconds shorter, and so forth. And it changes. These lines are maybe monthly. So the length of the day is really a rather erratic thing.
You said that this is caused by the Earth's rotation slowing down or speeding up. What's doing that?
This is caused by Earth's rotation slowing down. The fact that the long-term trend is up. The fact that they have all these wiggles, those are many other effects, which we are about to discuss.
Okay. Peace.
Okay, so this is where they get the measurements. And I'm not saying these numbers are terribly precise. And in fact, the authors don't do the usual scientifically proper procedure of quoting the uncertainties in their numbers. They just give the number, which is not a good way to do business, but anyway, that's what they do. Okay, so you can measure the slowing down of Earth's rotation by looking at historical records of when eclipses occurred, where and when. So the ancient Greeks famously recorded that on a certain day there was a total solar eclipse at dawn. Well, that defines a time and a place, and we can run our computer clocks backwards, and we can figure out that if Earth's rotation had always been 24 hours a day, that they wouldn't have seen that at dawn. They would have seen it at 6 hours later or something. And so the explanation is that Earth's rotation is slowly slowing down by this rate. So there are many recorded eclipses in the past. It was an event that all peoples and many different societies considered a dramatic event worthy of note. And so if you go through all the recordings, this is the average number that you get. In the era in which there have been good telescopic observations of the heavens, that's what this word refers to, then we get a significantly larger number. But it's a different time period, so and as we can see, the rotation has been erratic, so maybe that explains that. This is another telescopic observation. Lunar occultation means that the moon has, as we look at the sky, we see the moon moving over a star. The moon blocks the star, occults the star. And astronomers have kept track of that. And we can run the clock backwards and figure out how much the day had to change in order to explain the observations. And you get quite a different number. This is this international organization that keeps track of the length of the day, and they've existed for about 60 years, and they come up with a different number, but we saw that in the current age, the rate of the day was relatively flat. This is nanoseconds, this is microseconds, so this is 1,000 times. First of all, it's 10 times less than that, and it's 100 times less than that, and then it's 1,000 times less because it's a nanosecond. So this is effectively zero. Then even more wild and crazy and possibly associated with very large calculation uncertainties, paleontologists claim that looking at the fossil records, they can estimate the rotation rate of the Earth. They see indications in shells that of what the rotation period was. I don't know how they managed to do that, but they claim to, and they come up with plus 16 microseconds. And people who monitor the change in sea level over the last 3,000 years, and I don't know how they do that either. This is again back to some sort of fossil records. They estimate that there's been no change. So you have a lot of different numbers, and perhaps the fact that they're all as different as they are gives you an indication that they're not very precise. There are others, but they are even worse, other measurements. Okay, so what changes the length of the day? What Mary asked, what are these different effects? And they fall into two distinct categories. One is external effects to the Earth caused by the moon primarily and by the sun. And these are called tidal forces. This is the effects of gravity of the moon and the gravity of the sun. And there are actually dozens of different categories of these tidal forces because the moon and the sun are moving in complicated ways. The moon's orbit tilts relative to the Earth's orbit, and the tilt goes back and forth with some very long time period, and on and on and on. So the sun also is moving a little bit because of the influence of Jupiter. So you get a very large number of different complicated ways in which these tidal forces act. That's one big category, the external tidal forces. The next big category is changes to the to the moment of inertia of the Earth. So Angular momentum is the momentum of an object that's spinning, and angular momentum is a quantity that's conserved in nature, unless you have an external force. And you express angular momentum as being the angular rotation rate, omega, how fast it's spinning, times its moment of inertia. So instead, linear momentum is the mass times the velocity. Angular momentum is the effective mass, if you will, times the rotation rate. And the effective mass is defined by this equation. If you take each little bit of mass within the Earth and you multiply it by the square of its distance to the axis of rotation. Now, r is not the radius of the Earth. It's the distance between that piece of mass and the axis of rotation. So if something is at the North Pole, its r is 0 because it's on the rotation axis. If something is on the equator, then it has a big R because it's as far away from the rotation axis as it can get. Anyway, you add that up over all the different pieces of mass on Earth, and that's the moment of inertia. So if you change the moment of inertia, then omega is going to change. Now, if you've watched the Olympics, for instance, and you see these ice skaters, and at the end of their routine, they typically will do this spin. And they start with their arms outstretched and they pull their arms in and their legs in. And what they're doing is reducing their moment of inertia. They're reducing their R. When you reduce R, you have to increase omega. So as the ice skaters pull their arms in, they're spinning faster and faster, okay? So the same thing would happen to the Earth. If you were able to pull material inward, the Earth would have to spin faster, which means the length of the day would be shorter. If material moves outward, then the length of the day becomes longer. The moment of inertia becomes bigger, so omega becomes smaller. And there are many ways in which the moment of inertia gets changed. So if you have, for instance, a big earthquake and one tectonic plate moves relative to another tectonic plate and a large amount of rock goes down, having a smaller R, then that will speed up the spin of the Earth. If, on the other hand, you have a lot of material that when the ice melts on the poles, the moment of inertia for the ice on the poles is almost 0 because they're on the axis of rotation. But when all that water is released to the ocean, the ocean is far away from the axis of rotation, right? It's as far away as you can get at the equator. You've increased I, and therefore you've decreased the rotational frequency, increased the length of the day. So there are all these effects. So let's talk about the tidal forces. The moon's tidal forces on Earth are 2.4 times stronger than the sun's. So they dominate, but the sun is not insignificant. The total impact of all the tidal forces, which we can more or less calculate relatively precisely, is 24 microseconds per year. Now, we said that the change was 18 microseconds per year, the change for all effects. So most of the fact that the Earth's day is lengthening has to do with the moon's tidal effect, slowing down our rotation rate. And everything else works in the opposite direction, but is not as big an effect. The major tidal force of the moon is called lunar M2, and that's just the fact that the moon is pulling on Earth with a different force on one side of the Earth versus the other side of the Earth, which causes the crust of the Earth to go up and down by as much as half a meter. as the moon goes around. We see that the water flowing, but we are not as sensitive to the fact that the rock of the Earth itself is also flowing. This is, for those of you who don't like meters, that's about 1.6 feet. Okay, for every force, Newton said, there's an equal and opposite force. And so the Earth has an effect on the moon in the same way as the moon is causing tides on the Earth. And the effect that the Earth has on the moon causes the moon to move away from the Earth. And the Earth is moving away, the moon is moving away from the Earth by 38 millimeters per year, which is a little bit more than an inch. 30 millimeters is about 1 inch. And we measure that very precisely because the 3 sets of Apollo astronauts and 2 unmanned Soviet missions put laser reflectors on the surface of the moon, and we blast a laser beam at those reflectors, and some small amount comes back. 1/100 of a billionth of a billionth of what we shoot out actually gets bounced back to the Earth. And we've done that 20,000 times. And so we have a long history of measuring very precisely that the moon is moving away from us at about 1 inch a year. So these are all the tidal forces. They amount to 24 microseconds per year. Now these are the other category, the changes in the Earth's moment of inertia. So we talked about the melting of the ice caps, which raises the sea level. The combination of that should add 6 microseconds per year. It's increasing the moment of inertia, which makes the rotation rate less, makes the day longer. This is atmospheric effect is very small. I put this in just to be complete. And for those that care, this is the mass of the atmosphere. These are changes to the actual body of the Earth itself, and in the crust and in the core. And this has to do with the upwelling of lava and so forth. And this is a calculation that also is lengthening the day. And this is glacier rebound. So the glaciers have melted. The last ice age ended several 10,000 plus years ago. And when all of that ice was came off the land, the rock is actually lifting upward. It was compressed down by the weight of the ice. The ice is gone, so the rock is rebounding, and that's increasing the moment of inertia. So you get a combination effect, and they measure -11. They compute -11. And I think these numbers have substantial uncertainties, but if you add them all up, they add up to very close to 0. You've got +6, +5, -11, close to 0. Okay, to just say a few more words about why the moment of inertia changes. So polar ice increased, according to this agency, international agency, for much of the 20th century, but as we know, the ice is rapidly melting now, but did increase for many of the decades of the 20th century. The last ice age ended about 20,000 years ago, and at that point, the sea level was 125 meters lower. That's a dramatic number. That's like 500 feet lower than it is now. And because all of the water was tied up in the ice on the land. And after the melt, the rock is flowing up, and it's also flowing toward the poles where the ice has been removed. And you can actually see the land mass moving each year. The most dramatic effect is in the Hudson Bay in Canada. You see that the rock is moving by 1 centimeter per year north. And all of that affects the moment of inertia of the Earth. Okay. Any questions about the moment of inertia? Or, I mean, the length of the day? Okay, let me, just in a couple minutes, there's not much controversy about this. This is the computer that ran the Apollo space mission. It's called the AGC. It was designed by MIT, and it was a single purpose computer to control the spacecraft and to help it navigate. And this is the capacity that it had. These are kilobits, not kilobytes. So you divide by 8, that would be 9K bytes of ROM. That's the program memory. And that would be 500 bytes of RAM. That's the random access memory is what you where you store the variables. The program doesn't change, so you hardwire that. And the computer operated at a blistering rate of 14,000 floating point operations per second. Modern computers are in the trillions of floating point operations per second range. The computer operated with a 16-bit word, 15 bits of data, and 1 parity bit for in each word. This is the reference to the article, the technical article produced by somebody from NASA, published January this year. This is a picture of Apollo 11 coming back to the lunar, this is the lunar module coming back to the main transfer vessel that came back to Earth. And that's Earth in the background. This is the surface of the moon. Great picture. Now, this memory, program memory, was hand wired with magnetic cores. So you had these magnetic cores here, and the wires either went through or around each of the cores. And in doing so, they defined either the bit being on or the bit being off. And so wire A, which misses this core but goes through these 2 cores and misses the last one, wire A, well, I did this wrong. This should be a 1 as well. So that's a 4, that's a 2, that's a 6, and this is a 9. So that's how you make numbers by wiring these things. And there were thousands of these magnetic cores and many thousand wires. And some people wired threaded the wires through the cores by hand. And if the programmer wanted to change the code, they had to start all over because it was impossible to unwire. So why did they do this? Because they didn't have any better technology. And this turns out to be extremely compact. You get a lot of code for relatively small space and weight. This is the control panel for the computer. So you have important things like the tracking, the program, the gimbals, altitude, velocity, and there were a whole series of operations that the astronauts were able to do, and they defined a series of verbs and a series of nouns. So a verb might be turn on, and the noun might be the main motor. So they would type in a number and hit verb, type in a number for turn on and hit verb, type in a different number for main motor and hit noun.
Back in the day, I worked on compilers that knew about those verbs and nouns.
Yeah, I see. Okay. Well, you know, people didn't understand computers back then, right? I mean, these astronauts were jet pilots. They weren't computer geeks.
I remember being called in and said, okay, we want you to write this little interpreter that has these nouns and these verbs. Okay. That was a long time ago.
Yes. This is a long time ago, right? This is the 1960s. And how did it work? Well, in some ways, remarkably well. when they were landing on the moon for the first time, the computer flashed this, continued to flash this unidentified error code, which disturbed everybody just at the wrong moment in time. But the computer still managed to provide, still seemed to be providing the proper guidance and maneuver control. So NASA and Neil Armstrong decided that they would continue with the mission despite the computer going nuts. And indeed, as we all know, the module landed just fine. And later they found out, after the whole mission was over, the investigation uncovered why the computer was flashing this error code. And that was that there was a radar dish that was inadvertently left on that was supposed to have been turned off. And the radar dish was continually accumulating its data and into the very small random access memory that the computer had. So that memory was continually overflowing with this junk data. And every time it overflowed, there was an error code that got flashed, and the computer automatically rebooted and restarted and continued the mission. So the great part of this was a fail-safe design. So even though the computer was being crashed, it gracefully came back and kept running. You know, that's better than the computer I have on my desk. When it crashes, you know, all hell breaks loose. Okay, that's the end. So anybody have any questions or comments about any of the things we talked about today?
The only comment I want to add is that when we first started working with those small computers like that didn't have a lot of memory and not a lot of space, that people got very, very creative
Yeah,
about how they use that space.
yeah,
The gyrations we went through to take memory out and put new memory in and put this and that in, just to be confined within that 64K kilobits or whatever space we had, was phenomenal. I mean, we spent an inordinate amount of time figuring out how to manage all that space.
yes.
And those errors codes that came in, we had exhaustive tests on those computers, and we had to test every boundary condition, and we had to have a way to get it out of that boundary condition, whatever it was. That's why that computer could reboot, because somebody had figured out that it could overflow, and if it overflowed, this is what we wanted it to be done.
Yeah.
And we had to go through endless tests about all the what could happen, and we had to build it all into this small space of programming. It was quite a challenge. It was fun, a lot of fun.
You guys did a great job.
Well, there was one generation after another generation after another generation, and we all learned from each other. It was just phenomenal.
Yeah.
I remember for my master's, I had to write an HP 2100 computer simulator, because the purpose of that was so that we could write this code in non-demanding environment, that we could try to figure out how to use the limited space.
And test it.
Yes.
In a way that you could redo it easily, as
We
opposed.
didn't have any sophisticated debugging thing. We had to do what was called desk debugging, which means if we had an error, we had to take the stuff back to our desk and figure out what went wrong. We didn't have any highfalutin assistance on how to tell us what went wrong. So we had to use our brains. It was all, and so we had a team effort to try to figure out how to do all this stuff. It was quite thrilling. It was quite challenging. I came in at the tail end. I had a lot of big shoes that were ahead of me that knew what to do. 2 or 3 women I worked with were phenomenal in doing some of that work. Very, very creative. When we launched one of the satellites, I remember I was at school, and I had come in and I worked at nights, and one of the women was pacing the floor, and her name was Karen. And I said, what's going on, Karen? She said, oh, I'm really worried. What's going on, Karen? She says, my code is the one that opens up those solar panels. Those solar panels don't open, nothing works. So she was just waiting for that thing that said solar panels deployed. She just went, oh, it worked. But we had done exhaustive testing to make sure that would not fail. because if it failed, we lost $1 billion system. That's the kind of stuff that was,
And
It's
make
very
it
exciting.
nuts.
it was very exciting to work in that kind of environment. Yeah.
Yeah. Well, that's great to hear. Thank you. Anything else, guys? Okay, well, today's seminar was, as I said, to try out something a little bit different. So I'd be very interested in your feedback on whether you liked a whole bunch of little topics or you prefer something else. Next seminar, we'll talk about dark matter, and it'll actually take us 2 seminars to cover dark matter, but the first seminar will be about all of the evidence that we have that there is something out there that needs to be described. And the second seminar will get into more detail about the experiments that have been made and what are the crazy ideas people have as possible explanations. And let me assure you that these ideas are all really off the wall. There have been published just in 1 year, 2,600 different research papers were published on the subject of dark matter. 2,600 research papers. And the one thing that we can all be assured of is that 2,599 of those are wrong, because there is only one right answer, and the best we can hope for is one of those papers has that right answer, but probably not. Okay, thank you very much, and we'll see you in 2 weeks.
Thanks. See ya.